Welcome, everyone. We're up to almost 50 attendees so far for today's session on monitoring and understanding trends in surface, radiation, clouds, and aerosols. And we'll be starting our session in about 2 minutes. Okay, let's get started with our session today. Greetings to all of our attendees and presenters, and welcome to the second virtual Global Monitoring Annual Conference, otherwise known as eGMAC session, hosted by NOAA's Global Monitoring Laboratory in Boulder, Colorado. And as you can see, due to COVID-19, we're trying this new virtual format this year as a way to share our latest science even during the pandemic. My name is Diane Stanitsky, and I am chair for today's session. Our session focuses on monitoring and understanding trends in surface radiation, clouds, and aerosols. And in this session, we'll have 6 20-minute presentations, with each speaker having 15 minutes for their slides, followed by 4 minutes of question and answer, and then 1 minute for a transition from one speaker to the next. Everyone who's attending is invited to ask questions of our speakers, and you can do that by typing your question in the question box that you see in the panel on the right. Please feel free to type in your questions during the presentation, so each of the speakers can be ready to review those questions. And we do have 2 question moderators today. The first is Laura Riamaki from the Global Monitoring Division. She will be the question moderator for the first 3 radiation-focused talks. And then Patrick Sheridan, also from GML, will be the moderator for the last 3 aerosol-focused presentations. And they'll be noting your questions, and then as time permits, they'll communicate them to the speaker during the Q&A period. We'll try to get through as many questions as possible. And just to let you know, all questions will be saved, so the speakers have an option to respond offline to those that can't be addressed today. And another option is for you to raise your hand by clicking beside the name in the attendees list, beside each of your names. And the question moderator can unmute you so you can actually ask your question verbally. So look for the little orange hand, and in that column, you can just raise your hand if you do want to ask a question. Throughout the session, all attendees will be muted. And just so everyone knows, I'll plan to give a verbal cue for our speakers when there are 2 minutes left to their presentation time, so they can start making their final summary statements. And finally, today's session will be recorded and then available online for future viewing, along with each presenter slide set at the website where you registered for the eGMAC series. And if you refer to the agenda, you'll also find that URL in the attachment that you see in the handout on the right panel. And there you'll find the URL where you can find the recording afterwards. James Salzman is helping us today. He's our IT guru, and he'll be supporting our speakers behind the scenes. So without further ado, it's my pleasure to welcome our first speaker. That's Dr. Chris Farrell. Chris is a research physicist in the NOAA Physical Sciences Laboratory in Boulder, Colorado. He's been at the lab since 1989, and he has spent decades developing and deploying air-sea interaction observing systems on NOAA ships and aircraft and has participated in nearly 50 research field programs and cruises from the tropics to the Arctic ice cap. So Chris, welcome and thank you for kicking off today's presentation and session with your presentation, Solar and Infrared Radiative Flux Observations from Research Vessels and Buoys. Chris.
All right, thank you very much. Let's see. There we go. So let me back up here. Let me try to back up. All right, there we go. So I'm going to be discussing the solar and IR radiation measurements from ships and buoys. I'll give you a little background, discuss the issues with ships and buoys, talk about the flux reference buoy sites analysis, and then a little short note on future. Looks like we have a pretty good delay here. I hit the forward.
Make sure, Chris, that you've clicked in the window because I don't see the slides have advanced at all yet.
All right, there we go. So this is an example from the early 90s in a program called Toga Kohler. And we did an in comparison with 4 ships. 3 of the ships were side by side for 1 day, and the other one was sort of going back and forth. And on the left upper panel, you can see solar flux from the comparison for 1 day. You see blips downwards, like in the green and the black. Those are clouds that were affecting one ship, but not the others. And you can see some disagreements there. And on the right, you can see the IR flux. And these were the values that people produced when we got together a year later to compare. And then we went through a process to rationalize the differences and do the corrections. So when you look in the lower left corner, that's the corrected solar flux from the 4 ships after we did these corrections. When you look in the upper right, you'll notice the IR fluxes. 3 of the ships have substantial contamination from solar flux because they weren't where they needed to do corrections for dome heating. And so we were able to correct all that, and that shows up in the lower right panel, the final results. So some basic issues with marine measurements. The buoys are unattended for a year, and there's about 10 watts for everything, so you're pretty limited. The ships, you've got plenty of power, but you have superstructure in the field of view, you have radio interference, you have competing calls on real estate, so you can't just put your stuff where you want to. You can get reasonable maintenance on the 1-month field process study if you send your own person, but if you just leave it on the ship for a year, the maintenance is fairly limited by their staff. On ships and buoys, you have pitch and roll and heading variations, so you can't use conventional sun trackers and shadow bands. You also have sea spray and biological contamination of the optics. And then over a year, of course, you have sensor calibration discs, etc. So we use conventional pyranometers and pyrgeometers, pretty low-tech devices compared to BSRN methods. And this is examples of the sensors used. The solar fluxes are simple thermopiles, so you measure from 0 to 1200 watts. On the right here, the upper panel, you'll see the system that's deployed on the buoy. In this case, the buoy is parked on the deck of the ship and it's tilted over. That's why they're tilted. In the lower right hand, you'll see a setup on the ship. You can see a cluster of buoy sensors which are not being deployed. They're just being compared. Then you see 4 other sensors, which are our systems. And over here, you have a thing called a spin one, which is a different technology. The solar fluxes have issues with them from these simple devices. There's a thing called a cold sky bias I won't discuss. and a non-cosine response. They're not perfectly cosine responders. And the infrared flux, there's also a thermopile and a voltage, but the thermopile in that case acts sort of as a net IR flux radiometer. So you have to add in the sigma t to the fourth. And there's also this third term here, which is a dome heating thing, which has a second coefficient B, which is on the order of 3. And so that can represent as much as a 50-watt error. All right, so whoops. Here we go. Sorry for this. So calibrations, you can rely on factory calibrations, send them back and let them calibrate every couple of 1 or 2 years. You can use facilities like the picture shown on the right here in Boulder, or you can keep your own secondary standard if you have a big operation, which is what Woodsole has been doing. Some notes on calibration though, Epley uses what's called an integrating sphere of light bulbs, and so they don't include the cold sky effect. And GML, when they do their calibration, they set the solar sensitivity as the value at the 45-degree solar incidence and clear conditions. And if you get calibrations from Epley, they give you the thermopile coefficient only. They don't give you that dome coefficient, which is important. So we now work with the GML group, and you can do calibrations. This is an example of one of our, or a couple of our IR sensors calibrated against their reference. And if we use the Epley thermopile coefficients, we get the kind of fits you see here on the left. And if we adjust the thermopile coefficients to get the best fit, you get what you see on the right. So what we now do is use the calibrations against GML to determine the thermopile and the dome coefficient. So you can hear dome coefficients here about 2.7. So a factor with the solar calibrations is that you have a cosine effect and a non-cosine behavior. And so if you break the solar radiation into a direct beam, the beam and the solar and the diffuse, then you can look at the non-cosine behavior. And here on the right, I'm showing there's 4 Epleys here in green, and they have a significant non-cosine behavior. So that's something that has to be taken into account to get the most accurate results. And so I won't go through the details, but I'll just let you know that in principle, that can be taken care of. And as far as pitch and roll on ships and buoys on a ship, you can use a stabilizer, this one here that was built by Sergio Pizzo in the lab here. And here it is in operation on the Ron Brown, and you can see the ship is rolled over about 5 degrees here, and there you can see the platform and the horizon. It's almost perfectly level. So this is a method that works on ships. So now a word about these, the buoys. This is one of these flux reference buoys. There's 3 of them maintained by Woodsole, one here off Hawaii, one off Chile, and one in the North Atlantic. And this is the Ron Brown here. So we have a program where we, when they service the buoys once a year, we have our flux system on the ship and we do inter-comparisons. And the idea is that we're providing a quality assurance program for these buoys. Another point about these buoys is they're in these gyres out in the ocean. They're at least 1,000 kilometers away from any continent, and they're in the gyres where the boundary layer air is kind of circulating around the ocean and never goes anywhere close to land. So these are like perfect climate reference stations. So nobody's going to build a skyscraper next to your buoy, or they're not going to operate a copper smelter or anything like that. So these are like the cleanest, most pristine sites on the planet, as far as I know, except possibly the South Pole. So this is an example of evaluating the time series from the stratus buoy. So here you see the solar IR flux, the air temperature, and the specific humidity. They have nice long time series here, about 18 years in this case. And there's a big annual cycle. So if you remove the annual cycle, you then see the monthly values with the annual cycle removed for solar flux, IR flux, cloud fraction, which is estimated from the IR flux, and air temperature, and these lines on here are linear regressions through them. And here's a table of the trends from the 3 sites, the Stratus, INTAS, and WATS. And down below here, we're just comparing the solar and IR flux, the nets at the Stratus buoy with ERA 5 reanalysis. And you can see the reanalysis, which is sort of considered the, this is one of the better reanalysis, is significant flux errors and radiative flux at this particular site on the order of 15 to 20 watts. So you can also, on the right-hand graph, I've graphed the variations in cloud fraction against the variations in IR and solar flux. So you'll notice you have a positive fluctuation in cloud fraction, then you're getting more IR flux and less solar flux. So the majority of the variation in fluxes with the annual cycle removed is driven by cloud variations. No surprise, but relevant to this analysis. And in these tables, I've just shown you the change per decade of the solar and IR flux at these 3 sites. So in these cases, the solar flux and the IR flux are both increasing. They're at the edge of the statistical validity. So finally, just for the future, for buoys, kind of keep doing the same thing, but use a modern technology instead of Epley's, and eliminate the cosine, non-cosine behavior, add this spin 1 to get diffuse flux. On ships, you should be pitch roll stabilizing, but use the same kind of technologies. And if you wanted to, you could do some research with a pitch roll heading stabilize and put some BRSN technology on one ship, for example, and do some studies. You can get the buoy data from this site here. You can get hourly, daily, and monthly values, and you can get our ship data from this site. So with that, I'll conclude. Thanks.
Thank you, Chris. That was a great presentation. So if you have questions, please put them in the question box, or you can raise your hand and I will unmute you. So we've got one question here from Jim Butler. Chris, the platform looks good for the sensors on the ship, but you mentioned that you were showing a 5-degree roll. What happens at 25 degrees or 35 degrees?
Well, you get lousy data. So the buoys that we're talking about are pretty big buoys, and they have a very taut line and a lot of weight on the line because there's many sensors on the line underneath in the water, and they don't pitch and roll very much. And most of the time the ships are out there, the pitch and roll is less than 10 degrees, but certainly in high latitudes and in storms, pitch and roll is an issue. So you really need a stabilizer if you really want to believe the radiative fluxes in storm tracks and higher latitudes. And incidentally, the time response of these sensors is like 5 to 10 seconds, so you can't measure and correct later.
And another question, Chris, what temporal resolution are you is most possible and scientifically useful on ships or buoys?
Well, for radiative fluxes, I mean, we digitize at something like 2 hertz, and then we typically average to 1 minute. So we actually record 1 minute average data. That's probably, for the sensors we're using, which have like a 10-second response, that's probably as fast as you need to do. You can get some information out of the 1 minute data if you look at the statistics of the variability. You get some information on cloud behaviors and cloud fraction and things like that. But when you average up to 1 hour, then you start missing part of the diurnal cycle and solar. So you definitely want to save averages that are less than 1 hour. 10 minutes is good.
We've got a few more questions here. So 3 watts per meter squared per decade is a lot of change. Global greenhouse gases are 3 watts total since 1800. So how widespread would this trend apply?
I would say not widespread at all. I think it's specific to the sites. And if you average that, that's about what you get. I can't rule out the fact that it's some of that trend is due to the measurements. So I can't absolutely guarantee that there isn't some time-dependent bias in the solar flux measurements. Although, we've done our best to use the same systems the whole time and the same calibration methods.
We have time for one more question, Laura.
I have to pick now. Okay. So we've got a question. How close are you able to close the surface energy budget from the buoys?
So Bob Weller's done a lot of work on that. You can, from the measurements done on the buoys, you can't close the budget because you can't account for transport on the ocean side, horizontal transport on the ocean side. So typically, if you take the kind of budget closure we're used to doing over land, you'll often see imbalances in the 30 watt scale. And that's accounted for intellectually anyway by how much the ocean is moving by you. And so mean gradients can be accounted for in some ways. And then there's an additional eddy correlation. So eddies can transport heat horizontally that aren't accounted for in the mean gradients even. So it's a kind of a nasty, it tells you something about what the ocean is doing, is what the imbalances are.
Chris, thank you. Yes, thank you so much for your excellent presentation and for your responses. And we appreciate all of the attendees' questions. Those that weren't answered, we will be keeping track of so that Chris can answer them after the fact. Okay, we will turn to our second presenter, and that is John Augustine. John began his career at NOAA in Boulder in December of '77, just out of Penn State with degrees in meteorology. And for the first half of his career, he worked in weather research, first with satellite applications, and then research in mesoscale meteorology. And for more than 25 years, he has developed and operated NOAA's National Surface Radiation Budget Measurement Network, known as SURFRAD. So John's presentation is an examination of dimming and brightening over the US through 2019. John.
Thank you, Diane. So I'm going to talk about the dimming and brightening over the tenure of the SURFRAD network. Okay. All right, here it is. Brightening and dimming trends of solar radiation are global and multi-decadal in nature. This is a summary from Martin Veald's BAM's review of brightening and dimming, and it shows that it is indeed global. We have trends from the US, Europe, and a number of Asian sites. And from the 50s to the 80s, there was dimming over the whole globe, essentially. These trends are in watts per meter squared per decade, so they're not trivial. And then in the 80s, in the mid 80s to late 80s, it turned around and there was pretty much brightening everywhere. Martin shows it everywhere but India, and he attributes that to aerosols in India. But then after 2000, in Europe and the US, brightening continued, but in Asia, it started to change. So it is indeed decadal in nature and significant. Since 96, SurfRad started in 1995, but 96 was the first viable data to use in this type of analysis. We've been documenting surface radiation trends using this SurfRad network. And I want to just point out here that you can see by the map that it's climatologically representative of the US. And these are the results of solar at the surface. What I'm plotting here are network average annual anomalies. And that's in the dark curve here. That's a network average. And to show the variability in that average, I plotted the individual stations time series in the colored lines. And you can see that from the start of the network to 2012, there was continual brightening. And if you'll notice, the change from here to here is roughly 12 watts per meter squared. So that is very significant. It's on the order of 3 times the doubling of CO2 in radiative effect. So it is very significant, and that rate was 7.4 watts per meter squared per decade. In 2013, there was a precipitous drop. The network average reverted to about the network or the long-term mean, and it oscillated around that for about 5 years. And then in the last 2 years, 18 and 19, it dropped. So that culminated in a new dimming trend of about 4 watts per meter squared per decade. So that raises the question, what causes these trends in solar radiation? There's a lot of literature, but I have found no consensus on what causes it, except that everybody agrees that the source of the variability is not at the top of the atmosphere. It's not in solar variation. Studies have attributed surface solar trends to aerosols alone, clouds alone, or the combination of both. Alternately, decadal variations in the circulation patterns could systematically affect cloud cover. That's been mentioned. So for the US, we had to determine if it was clouds or aerosols causing the brightening and dimming. So to look at clouds, we do measure cloud fraction. We don't measure, well, we measure cloud fraction with TS, with total sky imagers, but we also compute it using rad flux, which is Chuck Long's analysis. And what I've plotted here is the cloud fraction annual anomaly. So the 0 represents the long-term average. And just like the previous graph, the dark curve represents the network average, and the thinner lines represent individual stations. And you can see there's a lot of variability here. But what I've done was separate out the brightening period and the dimming period. And you really can't fit a trend line to this. I tried, and it came out to be not significant because of the variability. So what I did was I just compared the bulk average cloud fraction anomaly of the brightening period, and we get about 1% less than the average. And then I did the same for the dimming period, and I got plus 1.24%. So there, in the average at least, there was a jump in cloud fraction between brightening and dimming periods. Because of the variability of this, I put the standard deviation in these vertical bars. And you can see that they overlap here, which means that these populations are not statistically different, but they're different in the mean. Now, when we look at aerosol optical depth, which we also measure at surf-rad sites, I plot the network average annual aerosol optical depth in these dots in time series. And what you notice is that aerosol optical depth over the US has been decreasing ever since the start of the network. And aerosols can affect brightening and dimming by either the direct effect or the second indirect effect of aerosol. Direct effect is just the backscatter from the aerosols. But Els and I, in our initial documentation of brightening, determined that the direct effect could only account for about 10% of the brightening during this period. But the second indirect effect affects clouds. And clouds are probably what's causing brightening and dimming, but are aerosols responsible? Second indirect effects as increased aerosols increases cloud area and lifetime. We documented that for the surf-rad network by plotting the mean cloud fraction versus aerosol optical depth. And this is for the whole network and got this nice relationship. Applying this to this period with the change of AOD from here to here, according to this, accounts for about a negative 1%, a 1% decrease in cloud area due to the second indirect effect, which is what we saw in the previous graph. But in the dimming period, if you apply this relationship for the difference between AOD from here to here, cloud fraction should have decreased by another 1/3% or so, but it increased by over 2%. So this tells us that aerosols are probably not causing brightening and dimming. Since those populations of cloud fraction overlap for the dimming and brightening periods, I looked at it another way, plotted AOD anomalies versus solar anomalies. And this shows that AOD accounts for 3% of surface variability, and cloud fraction here versus solar accounts for 62% of the surface solar variability. So with all this evidence, it's clouds basically, and not so much aerosols that are causing brightening and dimming in the US. So the question is, what forces decadal changes in cloud cover over the continents? At conferences I've been going to on climate change, I've seen a lot of presentations on natural variability of climate through like the PDO, AMO, ENSO, and other such things. And I've noticed, well, they have the PDO and the AMO have about 60 to 80 year cycles. And I noticed that they corresponded pretty well to those cycles for both of them corresponded pretty well to the brightening and dimming period. So I got the index data from PSL and plotted annual averages. Here are the PDO over about the last 100 years. The way I plotted it here, anything above the 0 is warmer than average sea surface temperatures in the Pacific, and anything below 0 are colder than average sea surface temperatures. And what I overplotted, this is the dimming period, this is the brightening period, and the new dimming period. I plotted solar trends for the US and Europe, and they pretty much align with when the sea surface temperatures of the Pacific are in flux. When they're in flux downward, we get dimming over the continents. When they're in flux upward, we get brightening over the continents. What I thought was really interesting was this new dimming period corresponded to this precipitous dip in sea surface temperatures, which is very analogous to the onset of the dimming period in the 50s, where it started with this dip here. So there could be something there. Now, if you look at the AMO, That's basic. It's basically sea surface temperatures of the North Atlantic, again above zero, warmer than average. Sea surface temperatures below, it's colder than average. And I plotted again for the dimming period, the brightening period. I overplotted the trends that have been measured for the US and Europe, and they correspond to periods when the sea surface temperatures are in flux downward, getting colder for the dimming period and getting warmer for the brightening period. The AMO is not as sharp as the PDO, and it tends to go up and plateau, go down, up, and plateau. Notice that the dimming periods start at the end of this plateau in warm temperatures, and that's happening, maybe happening over here. We don't know what's happening with the AMO, but it's gone up and has plateaued, and we're at the end and we're starting to see a dimming period. So that's very analogous also what happened in the onset of the dimming in the 50s. So the main question is, how do changing SSTs relate to weather and clouds over the continents? Well, weather is basically forced by temperature and moisture fluxes at the surface. And there's a lot of evidence in the literature that shows that the Northern Ocean SSTs have a profound effect on short-term variability of climate over the adjacent continents, particularly these during the periods when the temperatures are warmer, the SSTs are warmer than average, correlates to drought fairly well over the US at least. But there are plenty of other examples of how SSTs relate to continental weather. So the way I looked at that was I used reanalysis to reveal weather patterns associated with systematic changes in Northern Ocean SSTs. And I'm using 500 millibar geopotential heights in this example. So what I did was I plotted the height pattern, the average height pattern for the entire period of dimming and brightening that goes from 1950s to 2012. So that includes a dimming period and a brightening period. So the average 500 millibar pattern looks like this, which is predictable, low heights over the cold areas and high heights over the warmer equatorial areas.
John,
However, when you take the anomaly pattern for the dimming period, this breaks up into a three-wave standing Rossby wave. And you get higher heights over the cooling waters of the North Atlantic and the North Pacific. That sets up, I believe, these cooling sea surface temperatures sets up this Rossby wave. So you have high heights and then intervening, compensating low heights over the continents. So low heights over the continents, greater than average low heights over the continents, correlate to weather and clouds, and thus you get more dimming when you have this type of pattern. When you do it for the brightening period, this is an anomaly pattern for the brightening period, you get the opposite, which you would expect. You get warming waters over the North Atlantic and North Pacific causing mean troughs at 500 millibars over the oceans and compensating ridges in between over the continents, Europe and the US. A ridge corresponds to, or at least in a standing wave, corresponds to greater than average good weather, you could say. So a ridge, under a ridge, you get descending air. Descending air suppresses clouds, and then so you get brightening during this period. So in summary, brightening over the US that began in the 80s appears to have ended in 2012. A new dimming period may have started in 2013 and has continued through the present. Surface solar trends over the US have been attributed primarily to systematic changes in cloud cover. And evidence is presented that the decadal variability of North Atlantic and North Pacific SSTs force standing planetary waves that support brightening and dimming over the US and Europe. Thank you.
Thanks, John. That was a great talk. So I've got a number of questions for you here. So Lynn would like to know if there is any change in the instrument for cloud fraction between 2012 and 2013.
No. We actually use RadFlux to compute cloud fraction with an algorithm developed by Chuck Long that related diffuse measurements to TSI cloud fraction measurements. So there really haven't been any changes.
Nice, thank you. I have a question from John Miller. How well does brightening and dimming correlate with the PDO on a year-by-year basis?
Actually, it correlates very well with decreasing temperatures as characterized by the PDO, decreasing sea surface temperatures, much better than it does for the AMO. So I see a very good correspondence with the PDO, sea surface temperatures.
Nice. So Andy would like to know about, he has a suggestion that breakpoint analysis is designed to look for discontinuities in noisy time series and could be a useful tool here.
What type of analysis?
Breakpoint analysis. So I can send you that one and you can respond more offline maybe with Andy.
Is that Andy Jacobson?
Uh-huh.
Okay.
And a question here from Pat Sheridan. Have you tried averaging data from only eastern and only western sites? Moisture, aerosols, etc. are very different in the east versus west United States. Do you think this might help beat down the noise in your 7-site average data?
No, I haven't tried that, no. I did it earlier with other data. And I do, in the AOD data, I do see a difference between west and east. So he's probably right there.
And there's time for one more question.
Okay, we'll close off here with Jim Butler's question. So he says it's a very nice analysis and he wants to know if it's being written up for a publication.
Yes, it is. I wrote a paper including this, but the internal reviewer told me to split it up between the brightening and dimming part and then the meteorological analysis part. So I'm trying to submit the brightening and dimming paper now, and then I'll take that other half of the paper and try to put that into another publication.
Great.
Thanks very much, John. And thanks, Laura. Excellent presentation and really interesting analysis.
Thank you.
Okay, now we're going to turn to Girmar Bernhard. And Girmar has been involved in the measurement of solar UV radiation since 1992. He was the co-PI of the National Science Foundation's UV monitoring network between 1998 and 2009, when these instruments were integrated into NOAA's Antarctic UV monitoring network. And so fortunately for us, he's still involved in processing and interpreting UV data from this network. His presentation is called Trends of UV Radiation in Antarctica. Girmar.
Can you hear me?
Yes, we can.
Excellent. Well, thank you so much for this nice introduction. Before I get started, I'd like to acknowledge my co-author, Scott Sturley of GML, and also Patrick Disterhoff, who retired from GML last year. Both Scott and Patrick travel to Antarctica and make sure that the UV data collected there are of the highest quality attainable. So thank you very much. First, I'd like to start with a little bit of history. When the ozone hole was discovered back in 1985, people were concerned of increases in UV radiation and effects or adverse effects on the biosphere. However, back then there were no UV measurements available, and the NESF struggled to get a measurement network established. And my company, Biospectral Instruments, got the contract and developed instruments and deployed them. And the measurements basically started in 1988, and the network eventually grew to 7 sites shown on the map on top. Today, I will talk about the Antarctic site, South Pole, Arrival Heights, and Palmer Station. Well, back in about 2008, the NSF said, well, we are really an agency for transformative research and not funding long-term monitoring, so you have to find a different solution. And we are very grateful that NOAA GML stepped in and took on those measurements that continue until today. So the website of the old NSF Polar UV Monitoring Network and the new NOAA Antarctic UV Monitoring Network are still up and running. Of course, the NOAA is, the NSF is also, and you can go there and find the data and just Google Antarctic UV monitoring, and you should find links to both of those websites. The instruments that we use are SUV100 scanning spectrodiometers, and the principle is very simple. Light enters a cosine collector, gets dispersed in a double monochromator, and detected in a photomultiplier. The main measurement is the global spectral irradiance between 280 and 600 nanometer. Between 280 and 400 nanometers, of course, the UV. And we retrieve many data products from those measurements. And my focus in my talk today will be the UV index, which is basically a measure of the part of the UV spectrum that causes sunburn, and the total ozone column. So now fast forward to last year, 2019, where Richard McKenzie, myself, and several others published a paper showing the success of the Montreal Protocol in curbing increases in UV radiation. And the method that we used in this paper was pretty simple. We compared high-quality UV index measurements at 17 sites distributed around the planet with UV index data that were calculated from total ozone measurements or estimated from climate chemistry models that either represent the world expected or the world avoided scenario. So what does it mean? World expected means that the emission of ozone depleting substances are curbed in compliance with the Montreal Protocol. And the Montreal Protocol is, of course, the famous treaty that has been signed by every country on this planet to phase out substances that deplete the ozone layer. The world avoided scenario is a scenario where the emissions of ozone depleting substances continue to rise unabated without being controlled by the Montreal Protocol. And the rationale behind our paper was, if we can show good agreement between the measurements and the world expected simulations, which basically are the world we are living in, we can show that the credibility of the world avoided projections is good. So now let's look at a few results. Here are normalized UV index data from the South Pole for the spring period. We normalized those data because there were slight offsets between the different data sets, and we're really interested in changes over time and not in offsets here. So the blue curve here is the measurement, which, as I said, started in the early 1990s and continued until today. And you see quite a bit of variability, which is, of course, because of the ozone hole. The black curve is the UV index calculated from the ozone data, and you see very, very good agreement between the measurements and that data set, which basically tells us that the variability in the UV index is caused by ozone. Now, if you look at the world expected simulation, which is the green data set, you see an increase between the start in about 1975 and 1991 when the UV measurement started, but not much change after that. And in red and magenta are the world avoided simulations, which show large increases of about a factor of 3. Well, there are differences between these two simulations, which are based on different CCM models, but the slope from 1996 onwards is pretty comparable. The next slide shows a similar comparison for summer. Here you see that the two world avoided simulations agree better. However, the world expected shows some increase here. But overall, the picture is pretty clear that the world would be a very different place if the Montreal Protocol hadn't been in place. So next, we calculated trends per decade from those data sets of these 17 sites. So that plot shows trends as a function of latitude, and the Antarctic site, South Pole arrival heights, and former stations, of course, on the very left. And as you can see, trends in UV radiation between 1996 and 2018 ranged between about 5 and 10% per decade. However, trends calculated from the ozone data set are smaller, which is a little bit puzzling, but agree well with the world expected trends. And of course, the world avoided trends have a whooping change of about 50% per decade in the southern hemisphere, or Antarctica, I should say, and also pretty substantial in the Arctic and Barrow Summit, as you see to the right. The next slide shows similar data for the summer, again, trend per decade. And what you see here is that at arrival heights, there's actually a significant trend of 5.5% here, which again is larger than the trend we would see from the ozone, which is very close to zero. So the puzzling question is, why do UV measurements show a trend and UV index measurements calculated from ozone don't show a trend? Well, that paper includes the caveat, which I read to you. We also note that measurements at South Pole arrival heights and Palmer Station are potentially affected by long-term drifts of approximately 1% per decade, which are associated with hardware modifications and change in calibration standards. And I put that sentence into the paper because of the plot that you see on the right side here. It shows the ratio of measurement and radiative transfer calculations for clear skies. So these are models, not CCM models, but just radiative transfer models. And you see this decreasing trend from about 2006, 2007 to 18, 19. So every data point here is basically based on 1 year of data, and it's the median of the ratio of measurement and model for that year. And I show wavelengths between 310 and 400 nanometers here. And the model considers total ozone, but it does not consider surface albedo and aerosol, which are fixed. So a downward slope could mean that either the albedo has changed, the albedo went smaller at the South Pole, or that there's a problem with the calibrations. Well, I didn't find any evidence that the albedo has changed, so that points towards calibration. And a result of that, I have reviewed the whole calibration procedure of the existence of both networks here. And it's very technical, and I can't go into details here, but I want to focus on one aspect here, and that is the change in calibration scale over time. So all calibrations are traceable to standards of the National Institute of Standards and Technology, which are distributed via FELMs, shown here to the left. Between 1988 and 2007, we purchased standards from optronic laboratories that were calibrated against NIST standards. Around the time when NOAA came along, we changed to standards distributed by NOAA's CUCF laboratory. And when we compared the scales, which is the plot in the center, you see there's basically no difference. So very consistent. Then in 2012, we received 3 lamps directly from NIST and said, oh, that's great, let's use those lamps. And first we compared the scale relative to the previous scale, the CUCF scale, and it looked very good. That's the blue curve there. But unfortunately, it turned out that there is actually a change in scale of about 2% at 300 nanometers, tapering off to basically nothing at 500 nanometers. And for the UV index, that means that there is a step change of about 1.7%. So I corrected this and repeated the calculation of the measurement and model, and the results you're seeing here. So on the left side is the uncorrected plot, which you have seen before, and on the right side is the corrected plot. And as you can see, the trend between 2006, 2007, and 18, 19 is more or less gone. and the variability here is within plus minus 2%. That's about as good as we can do considering the uncertainties that are involved in those measurements. Well, the next step is pretty obvious. We calculated the trend from the earlier paper by McKenzie, and here the results for the South Pole. Spring is and summer is at the bottom, and I first like to look at the summer data set. So where I have my cursor now, that was the UV index trend as presented in the paper by McKenzie. The second data point is the trend based on the corrected data set, which is a little bit larger, as you would expect from the correction. I also tried a different correction, which is model-based, and I don't have the time to talk about that. And that's the third data point. The next points relate to trends in total ozone. And as you can see, these trends are positive, and the trend, the first data point here, or the fourth in total, is the trend as published in the paper by McKenzie, and the second one is the trend calculated from total ozone measurements of the SUV of instrument, which is larger, and finally the trend in the Dobson that is also at the South Pole. So as a rule of thumb, a 1% increase in ozone causes a 1% decrease in UV, and if you compare the increase in trend of the SUV in ozone with the decrease in trend of the corrected UVI, then you see it's pretty consistent. The last data point here, labeled E340, is the trend in the irradiance at 340 nanometers, which is not affected by ozone. And there's basically no trend, which means the confirmation that albedo hasn't changed at the South Pole. Now let's move to the plot on top. That's the trend for spring, where the ozone hole is, and you see large trends which are not statistically significant. And I forgot to mention that the error bars, the red one is 95% confidence interval, and the blue one is 90% confidence interval. So now let's move to the other side, survival heights and Palmer Station. If you look at the top row again, you see large trends which are not statistically significant. But the interesting part is the trend for arrival heights in the summer, where the UV trends are all negative and are all statistically significant. So making the correction didn't change the significance of the trend that was already pointed out in the paper by McKenzie. And there's basically no trend in ozone. But what's curious here is that there is a statistically significant trend at the irradiance at 340 nanometers. And so that's curious. So what causes that? Well, it turns out that it's an iceberg. What's plotted here is the spectral irradiance at 340 nanometers at arrival heights for March as a function of year. And as you see, there's a downward slope between about the year 2000 and 2010. Overlaid to that is the distance to the ice edge. And as many of you will recall, there was a gigantic iceberg sitting at the entrance to McMurdo Sound in the early 2000s, which increased the albedo tremendously because the McMurdo Sound was basically frozen over during this part of the year. And that means there's high albedo, incoming radiation is reflected upward, is partly rarely scattered down, and UV radiation is increased. So the trends that we see at arrival heights in spring are mostly related to this iceberg that lingered on for many years. Now I'm coming to my second to last slide. All trends I've talked so far are based on the period discussed in the paper by Richard McKenzie et al. And this paper was published in 2019, so it did not include the ozone hole of 2019. As a matter of fact, the last year considered for South Pole data was 2018, and arrival heights was 2017. And as you all know, the ozone hole of 2019 was one of the smallest on record. There was a press release in NOAA on the left side, and if you look on the right side, there's a plot of measurements of polar cap ozone by NASA in 2019 in red compared to the range of previous years. So when I recalculate the trends including 2019, the trends become more negative, as you would expect. More ozone means less UV, so the trend goes down. And none of those trends are statistically significant yet. However, the trend at arrival heights for summer increased, went from 4.5% to 3.9%, and is statistically significant. And I contribute this to the wearing off of the effect of that iceberg, which is long gone. And so the trends basically come up. Now let me come to my conclusions. The results confirmed the study by McKenzie et al. That UV irradiances at the 3 Antarctic sites has been decreasing between 1996 and 2018. However, trends for most months are not yet statistically significant. Decadal UV index trends calculated from data corrected for drifts and calibrations are 0.7 to 1.7% smaller than those reported by the paper by McKenzie. And for spring, which is the period September to November in Antarctica, statistically significant reductions in UV index have not yet been detected at any site because the ozone hole leads to large UV index variability. And it will likely take many more years until ozone recovery can be detected in UV data for spring, simply because it's unlikely that we will have a small ozone hole like last year for the years to come. Trends in the UV index are generally most significant for January and February. At the South Pole, significant decadal trends of -4.1 and 3.2% exist for January and February, and these negative trends may be partly explained by positive trends in total ozone. And at arrival heights, a significant decadal trend of -4.5% is observed for summer. It can be explained with a significant upward trend in total ozone of 1.7% per decade for January, plus the effect of changes in fast ice covering McMurdo Sound. And trends in UV index at Palmer Station were generally not significant. And I'd like to add that it is challenging to maintain a stability at the 1-2% level over 30 years of observations, considering all the uncertainties involved and also the uncertainty of standards we receive from the National Science Fund, National Institute of Standards and Technology. Okay, that concludes my talk.
Guillermo, thank you so much. We do have time for one question, Laura.
Okay, well, I have one. You did some really nice work correcting the data and understand where there were calibration issues. Is there any recommendations you would make for the future to make the measurements better in the first place?
Well, it's always a struggle in making sure that the calibration standards you have are consistent. The standards you get from NIST have an uncertainty of 1% at the time it leaves the facility, but they don't guarantee what that uncertainty will be at the time it's at your doorstep. And that's only one uncertainty that contributes to UV measurements. So I believe we just have to keep comparing lamps and keep good records of lamps and don't use lamps for a long time and compare new lamps back to those lamps to ensure that we have stability in calibrations.
Great, thank you very much.
Thank you, Guillermo. We'll look forward to your upcoming publication. Our next speaker is Dominic Heslin-Rees, and Dominic will present research he carried out as a master's student while at Stockholm University, and it's now in discussion in the journal Atmospheric Chemistry and Physics. Dominic's work focuses on Arctic aerosols and clouds. He'll now be undertaking a PhD at Stockholm University at the end of the summer. And his presentation is From a Polar to a Marine Environment, Has the Changing Arctic Led to a Shift in Aerosol Optical Properties?
Hi there, everyone. So I'm just going to run through just a quick synopsis of what the main findings. So we looked at long-term trends in aerosol optical properties in the Arctic. We found that the composition of aerosol particles had undergone a clear and significant shift in the past 2 decades. These trends indicated the aerosol was dominated more by coarse mode particles and most likely the result of increases in the relative amount of sea spray aerosol. So I'm going to now go through an explanation of these findings and the methodology. So some motivation first. So as we all know, the Arctic region is warming twice as much as the global average, a phenomenon known as Arctic amplification. The ranges of possible mechanisms. The primary reason is the reduction in Arctic summer sea ice, either cloud cover, transportation of heat from lower latitudes, and also the reduction in sulfate emissions in Europe in the past 2 decades has also played a role. This Arctic amplification can have effects on obviously the further reduction of summer sea ice and changes to atmospheric circulation patterns. So given the fact that aerosols exert a considerable influence on the Arctic, we wanted to have a look at the rate at which aerosol light scattering properties had changed on Svalbard in the past 2 decades. And we wanted to see if we could link these to any meteorological parameters or changes in sea ice coverage. So I'll take you to the monitoring site. So Stockholm University operates quite a lot of instrumentation up on Mount Zeppelin. So that's on the western edge of Svalbard, an archipelago in the north above Norway. Now the remoteness and altitude of the site means that there's minimal or it's far away from substantial contamination sources, and it's also part of a global atmosphere watch. So the inlet's on the top of the observatory, and then you can see we've got a Holer inlet which brings in air and which is comes into the nephelometer. So this is a standard piece of kit in aerosol science, and it's used. We can measure at 3 different wavelengths: blue, green, and red, and we measure the ability of airborne particles' ability to scatter light. So from this, we can get extensive parameters, for example, the backscatter coefficient and the backscattering coefficient, and then we can compute intensive parameters such as the backscatter fraction and the scattering Ångström exponent, which I'll explain now. So those are so given the fact that the scattering coefficient is dependent on the wavelength, and if we measure at more than 1 wavelength, we can then deduce the Ångström exponent. And if you want to think of the Ångström exponent as a proxy for particle size, so if the Ångström exponent is greater than 1, the aerosol is dominated by fine mode particles. And if the Ångström exponent is less than 1, it is dominated by coarse mode particles. And 2 main examples of this is mineral dust and also sea salt. So this is sea spray aerosol derived from wave action, either from the crest or from wave breaking and then inducing bubble bursting. So in combination with the aerosol optical properties, we also ran a back trajectory analysis using the high split model. The back trajectories were 7 days long, and they provide a detailed history of the air parcels arriving at Zeppelin. They were temporarily collocated with the nephelometer data, and from that we could get the latitude, longitude, and the mixing depth. That's the height of the mixing layer, the height at which substances, for example, aerosol particles, are able to be vertically dispersed. In combination with satellite-derived monthly sea ice concentrations, we could then calculate the residence times. So how much time each back trajectory spent over ice, land, and ocean. So this is just a little example of what we did. Sorry about the arrows. It wasn't like that before, but we've got an example trajectory here, and you can see that as it arrives at Zeppelin, we've got blue for the open ocean, green for land, and then we've also marked in where we calculated the mean of the back trajectory. So this one is labeled as northwest. So that means it's coming from the northwest, and we'll use that later on. And just to note that we only use the part of the trajectories that have traversed in the mix layer. We assume that that part has been influenced by aerosol emissions. All right, so some results. I'm going to go through the long-term trends in aerosol optical properties, a little look at the seasonal trends, break it up via seasons, and then we'll have a look at the back trajectory analysis, including the surface residence times, the wind speeds, and which regions, the regional contributions. So for the trends in the scattering coefficients, we saw a small positive increase in the scattering coefficients over the 17 years of data. So we analyzed that we got the and then for the intensive properties, we see a small decrease in the backscatter fraction, but a clear statistically significant negative trend in the angstrom exponent, indicating that the aerosol, as the angstrom exponent reduces, the aerosol is dominated more by coarse mode particles. And having a look at the seasonal trends, we see that so this is the relative increase, and we see that most of the relative increases, we see larger trends in autumn and winter in the scattering coefficients, and then the largest reduction in the autumn for the angstrom exponent. So just to summarize, we've got increases in the scattering coefficient, a strong decrease in the angstrom exponent. And if we look at previous studies, we see a reduction in elemental black carbon around the same period at Zeppelin, reductions in total sulfate concentrations, and also a decrease in the anthropogenic accumulation aerosol, so in terms of the size distribution, which is interesting considering it's interesting to see that there is a reduction in the anthropogenic aerosols, whilst also having an increase in the light scattering coefficient. So one way of explaining this is the role coarse mode aerosol particles play. And this is, I'm just showing work done by my supervisor, Paul Zeiger, and he showed that coarse mode particles did contribute a significant portion still to the overall scattering. So scattering is, the accumulation mode is normally influences scattering the most, but coarse mode particles, as you can see, particles above 1 micron are still playing a significant role. So what could be the reason for this increase in coarse mode particles, explaining the reduction in the angstrom? So there's a few hypotheses I have here. So an increase in mineral dust, the other type of coarse mode particle. Could it possibly be the retreat of summer Arctic sea ice, leading to more open oceans, and therefore increasing the production of sea salt aerosols? Or could it be changes in air circulation patterns, so an increase in the amount of southwesterly winds, for example, over the North Atlantic, bringing with it more sea salt aerosols. There's also increases in wind speed, and finally a decrease in the contribution of fine mode particles. So given that the angstrom exponent represents the relative amount of coarse mode particles to fine mode particles, it could also be to do with a reduction in fine mode particles. However, number 4 would not explain the increase in the scattering coefficient. So I won't discuss that any further. All right, so why do we think, or what is the evidence to suggest it is sea salt aerosols? So these are ternary plots I did. using the surface residence times, and on the edges you see ice, land, and ocean. And in the bottom corner, the bottom right corner, you've got the you can see that the back trajectories, which spent most of their time over open water, had lower angstrom exponents, suggesting that the reduction in the angstrom exponent was marine in origin. Could it be the reduction in Arctic sea ice? So for this, this is the history of the relative surface contributions. And for this, I fixed the sea ice concentrations at the 1999 level. So that's the dashed line, and the blue line is the progression of sea ice concentrations naturally. And yet, as you can see, there's minimal difference between the two. So we suggest that it is not the result of this new expanse of open ocean, primarily because it's still a considerable distance away from Zeppelin, where most of the 2 million square kilometers of open ocean are in the summer. So air circulations, could it be the result of air circulation? So this is the combined 17 years of data, and we can see the general Arctic haze period where we have increased contribution from the northeast. So that's in spring and December. So the northeast contribution increases, and then in the summer you've got the retreat of the polar front, and Zeppelin is often found outside of the polar front, receiving mainly marine air masses. So there's an increase in the southwest contribution. But let's take a look at the long-term changes. So A shows the surface residence times, and we see an increase in the amount of time back trajectories spend over open water. We also see a slight increase in the wind speeds along the trajectories. And for the contribution from different regions, we see increases in the northwest and the southwest, and then reductions in both the northeast and the southeast. And if we look at this on a seasonal basis, we see statistically significant increases in the southwest overall. So these were tested using the man-candle test and also a linear regression test. And we can see primarily in the autumn was the largest increase in the southwest contribution, and this coincided with the largest reduction in the angstrom exponent. And for all months, there is an increase in a western air mass contribution, and we see reductions.
2 minutes.
Okay, thanks. And then again, for the parameters for open water, wind speed, and precipitation, we see that the air masses at Zeppelin are getting wetter and windier. So can we link this to regional or larger scale weather phenomena? So we see that the Arctic, the AO index has shifted to negative anomalies. So one hypothesis could be that the negative AO is increasing the south to north transport. And that's been seen in other studies, which have shown more frequent North Atlantic contributions to Zeppelin. So in conclusion, trend analysis, we see increases in the scattering and backscattering coefficients in the last 17 years. We see a reduction in the angstrom exponent, suggesting more coarse mode particles. Oops, does it work? I can't get it to, okay. And then we see that this is the angstrom exponent is marine in origin, or the lower angstrom is dependent on open ocean. And then we conclude that this is the result of sea spray aerosol production due to changes in air circulation patterns rather than the retreat of Arctic sea ice. There we go. And we also see an increasing trend, an increasing west to east gradient in the angstrom exponent. So the western air masses having lower angstrom values and the eastern air masses having higher. And yep, thanks for listening. And there's a link to the paper that's out now for discussion.
Okay, thank you, Dominic, for the nice presentation. So I have a question here from John Ogren is asking a question. Are these findings specific to Spitsbergen, or do they apply to the Arctic in general? There are quite a few Arctic GAUSS stations with multi-wavelength integrating nephelometers, for example, at Barrow, Alert, and at Tixie.
I mean, the work I did was, I mean, I'd say it's specifically for Zeppelin, but Martine Colon, she's got a nice paper out exploring the trends in other Arctic sites, including Barrow and Tixie. But I can't remember exactly how they compare as well. But there has been other increases in the scattering coefficient at other sites, not just Zeppelin. Which, considering that the majority of other sites at lower latitudes are experiencing reductions in the light scattering, it is quite an interesting finding.
Okay, thank you. We have another question. Joe Sedlar is asking a question. The question is, atmospheric flow around Greenland and Svalbard are notoriously variable, driven by sharp contrasts in topography. Numerical models have difficulty resolving these local dynamics on the flow, which limits the validity of high split back trajectories. Further, the stability of the lower Arctic atmosphere is driven by the interaction between low liquid bearing clouds and surface properties. These phenomena also pose problems for numerical models. Do you account for these uncertainties in air mass footprint?
No, these have not been accounted for. But given the sort of range of the back trajectories, I mean, the local topology was just assumed to not play such a significant role. No, it'd be interesting to hear more. I'll read more about this though, because that's not been accounted for.
We have time for one more question, Patrick.
Okay, we have one more question, and this one is more of a philosophical question, I think. Do you think the changes in the aerosol optical properties in the Arctic will affect the frequency of cyclones in tropical countries?
Well, I wouldn't be in a position to answer this question. I'm sorry.
Yeah.
So, nonetheless, interesting though.
Okay, thank you.
Dominic, thanks very much, and all the best with your PhD research, which I'm guessing is a continuation of what you're doing and presented to us today. Thanks so much.
All right, thank you.
Okay, our next presenter is Maria Burgos. Maria has been working at Stockholm University as well as a postdoctoral researcher, and she and co-authors created a data set of in situ measurements of aerosol light scattering at different relative humidities. This data set was then used as a benchmark for comparing with 10 Earth system models, which is the focus of her talk today. Maria, it's all yours.
Thank you, Diane, for the presentation and for having me here. Yes, and as she said, I'm going to present today my research project where I will compare global climate models with in situ measurements in relation with water uptake by aerosols. So I've been working with Elizabeth Andrews, Paul Seeger, and Gloria Titos, together with many other collaborators of the modeling and in situ community. So to start with, we were interested in aerosols and climate, since aerosols have direct and indirect effects on the Earth's energy balance. They can scatter or absorb solar radiation, and they can also influence the number of cloud condensation nuclei. And in particular, we wanted to focus on the hygroscopicity, which is the ability of aerosols to take up water. And in doing so, they will change size and chemical composition depending on the ambient relative humidity, so that the scattering coefficient will strongly depend on the relative humidity of the surrounding air. This is important, this effect of water uptake, if we want to calculate climate forcing, and also if we want to compare or validate remote sensing with in-situ measurements. But for our talk, I want to link it with the improvement of Earth system models. So throughout my talk, I will be talking about the scattering enhancement factor, which is calculated by the ratio of the scattering coefficient measured at a given value of relative humidity, so we call it wet conditions, divided by the scattering coefficient measured at dry conditions. And the motivation for our work was to answer the question of, okay, so how well are right now global climate models representing the aerosol optical hygroscopic growth? And the results I will show here are a summary of our work that you can find. It's now under review in ACP, but we have the discussion there, so you can go there and check if you are interested in some parts. And one of our motivation was that we realized that, okay, if you check models, they seem to be doing well when they are reproducing the total aerosol optical depth. But if you take a closer look into the individual components, you can see that there are discrepancies between them. So here, with these two global maps, we are showing the fraction of aerosol optical depth due to water. And you can see how they look quite different. And actually, they are giving global annual averages quite different. ECAM5 is given close to 80% and GOCAR close to 40%. So we wanted to understand what's going on here. So as I said at the beginning, I'm going to be comparing in situ measurements with model output. So let me present first the measurements. The measurements I'm using here is a data set that we created in the first part of my postdoc. And we brought together measurements from over 26 sites of around the globe, accounting for many different aerosol types. So we analyze them in a standardized manner, and so that we can compare one to the other. And we created this data set. And one of our main results can be seen here, that is how the scattering enhancement factor is larger for Arctic and marine sites, and it's smaller for rural or desert sites. Yeah, so this is about the measurements. And for the models, we'll be using 10 models that we have divided into the what we call CAM family models. And this includes CAM Atlas, CAM 5, and CAM Oslo. GEOS family models that includes GEOS-Chem, GEOS-GOCAR, and MER-Aero. And 4 further models that are called Oslo CTM3, TM5, IFS Aerosols, and SALSA. So from these models, we got the absorption and extinction coefficients at different relative humidities. And for us, it's important 0, 40, and 85. And for the green wavelength, we are going to be using here. We also had the mass mixing ratio for 5 components: black carbon, desert dust, organic aerosols, sulfates, and sea salt. And for some models, we also had nitrates and ammonium. We will see that in a few moments. The frequency of our model data is hourly or daily values for the year 2010. And one important aspect is that the time coverage is not always coincident with measurements, because some sites were measuring or not during 2010, so it's not always the same. Then we will extract model data for the closest grid point of 22 observational sites. And we have used simulated surface data regardless of site elevation. So in this table, I wanted to summarize a bit some of the main characteristics of our models. So here we have our 10 models. We've got the chemical composition, and as I said, all of the models have the 5 basic components, and 5 of them have also nitrates and ammonium. About the mixing state, we've got internal and external, depending on the model. And the next thing is the hygroscopicity. So we've got the parameterization and the hygroscopicity factor, the value, for different chemical components. So the parameterization for the CAM models is based on Kappa Cooler theory. For GEOS models is modified GATS and OPAC. And the other 4 models have their own development. So they use different parameterizations depending on the chemical component. And then we've got several values of the hygroscopic growth factor for different components. And there's one in red when they don't assume that they grow with relative humidity. So the results I want to show here are the ones that are marked in light blue, number 1 and 3. So first I'll show a comparison of the model and measure scattering enhancement factor, and I'll show also some results with the organic mass fraction. And then I'll focus on a test case for model seasol hygroscopicity, where we are focusing on one of the sites, Graciosa, because of its characteristics. If you want to check some of the other results, then you can check out our paper, our discussion paper. So for the first part of the results I want to show, I'll be showing the F of RH, the model one versus the measure. And then I will also show the F of RH, the model one versus the organic mass fraction. And here it's important that we have several parameterizations that we can find in literature, some from Keane and Seeger, where they use organics and sulfates, that are the 2 components that we will be showing here for several sites. And also there's the possibility to use or to compare with more with other parameterizations that include other components, but we have not used these ones because not all the models have nitrate and ammonium, so we have just focused on organics and sulfates. So I will show this for the 3 sets of models. So first we've got CAM family models, where if we show the model versus the measure F of RH, we can see that the models reproduce the range in measure F of RH, and there's a good correlation coefficient, mostly for CAM and CAM Oslo. And when we compare the model F of RH versus the organism mass fraction, we find that CAM and CAM Oslo exhibit similar relationship between these 2 quantities, as suggested by our parameterizations from Keane and Seeger. Then if we show the same for the GEOS family model, we've got that this model, in contrast, show like an upper threshold here for F of RH model. So they don't reproduce the range that we see in the measure F of RH. But in spite of this, they still fall within the 30% uncertainty interval. And of course, the correlation coefficients are lower. Then if we compare with the organic mass fraction, we see that in this case, these models do not exhibit the same organism mass fraction F of RH relationship as observations. And then we can show the same for our last set of models, the last 4 models. And in this case, we see a diversity of behaviors. We find good correlations for some of them. And then we even have SALSA, where we find an inverse correlation. It's the only model showing this. And if we focus in the organic mass fraction, we can see how Oslo CTM3 and IF's aerosol agree well with the parameterizations. Then if aerosol simulates aerosol, which is dominated by organics. TM5 exhibits same tendency as parameterization, but it's overestimating F of RH relative to the organic mass fraction, and SALSA is behaving again differently here. So the second set of results that I want to show is how F of RH is varying with relative humidity. And before showing the results, I want to explain here that we'll be comparing with observational data and theoretical values for inorganic sea salt and sodium chloride. So you can find that the green line is the theoretical curve for sodium chloride, and the blue and the red lines are the curves for inorganic sea salt. And we've got the blue is called the hydration curve, and the red is called the dehydration curve as the relative humidity decreases. And then the black stars, well, they were stars, now they don't look like stars, sorry for that. These were sea salt events, so they come from observation. And for you to have an idea of the values, the magnitude of the values we're talking about, we've got that F of RH at this should be 50% relative humidity for the hydration curve is around 1.2, and for the dehydration curve is around 2. So yeah, let's see how our models lie within these curves. So we've got 5 of the models that are modeling sea salt as sodium chloride, since they lie with the gray line here, the gray curve. And we can see how TM5, this model, the blue one, is showing that no hygroscopic growth up to 45%. Then we see Geochem, IFS, Aerosol, and Salsa, these models here that don't assume the aerosol to be solid at 40%. And Salsa estimates throughout the whole humidogram slightly larger values, which may be an indication of smaller particle sizes. And in comparison, our other 5 models are modeling inorganic sea salt. So yes, at 40%, we can see some models which are closer to the hydration curve, or some models are closer to the dehydration curve. Then within the hysteresis range, that is kind of between 40 and 75, the models are between both of these curves. And when we go to highest values of relative humidity, we have a variety. So Atlas is showing the lowest value, while CAM and CAM Oslo show the largest value. And these 2 models are the only ones taking into account the hysteresis effect. So as a summary of my results, we saw that the model assumptions about water uptake at low relative humidity values are a significant factor. We saw that different assumptions about the hygroscopicity of sea salt explain some model variation at a marine location that was Graciosa. And some models assume sea salt can be represented by sodium chloride, while some other models do not assume this. GEOS family models assign too much hygroscopicity to all species except dust. And regardless of, that means that regardless of the simulated chemical composition, the resulting F of RH will be high, except for the dominated dust-dominated sites. And this is what is shown by the narrower range that we found for these models. Then one of the characteristics of these GEOS models is that they all use the global aerosol dataset to parameterize the growth. So this high F of RH is consistent with previous findings by Seeger et al. That showed that GATS overestimated hygroscopic growth at low relative humidities. So the conclusion is that we compare measurements of particle light scattering enhancement factors with a set of 10 Earth global system models. We saw high diversity in this comparison between models and measurements, and that's due to the variability in different assumptions that models do, and they relate to hygroscopic growth and chemical composition. We also used organic mass fraction as a constraint or a sanity check for this model F of RH. And we realized that other variables can have an effect or an important influence, such the mixing state or the aerosol mixing size. But the problem is that accounting for the exact contribution of all these factors was a challenge, and with our data, we were not able to dig more into it. So we had some results that I didn't show here. If someone wants to check them out, you can go to our paper discussion too. And we use this temporal collocation. If you remember at the very beginning, I said that measurements do not always measure during 2010. So for some sites, we could do a temporal collocation, and we did it to study how they behave in this case. And it did not appear to improve the comparison with models.
1 minute, Maria.
Thank you, Diana. And then we also studied what we consider dry, because it could be 0 or 40%, and that that also meant that could also influence our results. And a bit of insight of the importance of dry can also be found in our paper. So yeah, if you want to have a look to all these results, you can check our project website or our paper. And that was all for my part. So thanks for listening.
Okay, well, thank you, Maria, for that nice presentation. Understanding why the models are so diverse and the differences between measurements and models is very important. We have a couple of questions related to that. One of those questions is, was the spatial resolution the same for, or at least similar for all of the models? And how would that affect the results if they were not the same?
Yeah, the spatial resolution was not the same, but it was not that different. So it could vary between maybe, I think to remember, latitude, longitude could be 1.9, 2.5, or 2.3, something like this degrees. So it was not exactly the same. And the methodology that we used was to take the closest grid point. So yeah, that's what we did. But we don't know how it influences the results. So we know that if you've got a marine site close to the coastline, so it may influence where your site is and where you take the model grid, the closest grid point is. So that can make some influence with the results. But within different spatial resolutions from between models, that we didn't check. So yeah, I don't exactly know how much it's influenced. Yeah.
Okay, we have another question here. Would you expect the model measurement disagreements to also apply to relative humidity greater than 100%? In other words, how well can we expect the models to reproduce aerosol effects on clouds?
Okay, that part, we didn't look at it. So I guess if we are having differences at lower values, it will also influence for clouds and larger values of relative humidity. But I couldn't say anything in particular because we didn't have those data and we didn't compare to that. Yeah, so far we focus a lot on what is dry, mostly that on larger values. Yeah, so we only take FFR rates up to 85%. So that I couldn't say anything very specific, but yeah, we should expect that it's also influenced there.
Okay, I don't see any questions from the audience, so I will ask one. It seems like the SALSA model is a bit of an outlier, and understanding these outlier models is very important. So why do you think SALSA is so different from some of the other models? Is it the input size distribution, or exactly why?
Yeah, that's quite complicated to assess because we have so many parameters that could influence there. About the chemical composition, we didn't find many differences in relation with the other models. For example, at Graciosa, that is the site that we studied for sea salt, the chemical composition of salsa was quite similar. And then if you go, so the other big thing that could be influencing here could be size distribution. And we didn't have the data to actually look into it. And yeah, that's one of the big things that we should take into account, and that requires more work and a lot of data that we unfortunately didn't have at this moment. So maybe we should start looking at it. But yeah, salsa is showing quite strange results or different from the others, yeah. But we couldn't assess exactly what was it.
Thank you so much, Maria, and thanks, Patrick.
Thank you.
Finally, our final presentation today will be given by Andy Lambert. And I'm really sorry that we're at our final presentation because these have all been so interesting. Andy is a research assistant for Dr. Gannett Haller at the University of Utah's Department of Atmospheric Sciences. He's working in aerosol and air quality research. He graduated this May with his master's degree and will soon begin his career at the Naval Research Lab as a physical meteorologist. Andy's presentation is entitled Dust in the Great Plains and Northern Rockies, Trends and Influences from Land Use. Andy.
Thank you. Yeah, today I'll be sharing with you the results from my master's research looking at trends in dust in the Great Plains and Rocky states and investigate how those are connected to land use changes in those regions. So this is just a graphic that my wife designed actually that I think does a good job of showing the various roles of dust in the atmosphere. And it begins with winds that exceed a certain threshold, moving over unstable soils that produce the dust emissions. And these thresholds have been estimated to be around 2 or 4 or 7 meters per second, depending on the papers that you'll look at. But I will say the more recent, the literature, they set the thresholds at some of the lower limits there. And if you introduce a land use change, that would further reduce the wind speed threshold to make it more likely for dust emissions to occur. And when dust emissions occur, they take with them some soil nutrients that make it so the soil has a harder time with vegetation growth, and that starts a cyclical process which further destabilizes the soils and makes it more likely to produce dust emissions. And dust in the atmosphere does contribute to visibility reduction, and this is especially important for naturally pristine areas like wilderness regions and national parks. It also contributes to visibility reduction that creates dangerous driving conditions on highways and busy roads. And there have been deaths associated with dust storms and vehicle crashes. And dust has impacts on cardiovascular, respiratory, and among other health complications, especially for those who are sensitive. Dust interacts directly with solar and terrestrial radiation, as well as indirectly through its role as cloud condensation nuclei, or more often ice nuclei. And this contributes to the substantial uncertainty that exists in radiative forcing estimates in our climate models. And finally, when dust is deposited onto snow, it can lead to accelerated melting of mountain snowpack and strain water resources for those who are dependent on water from the snowpack there. So the main motivation for this research comes from a paper from McClure and Jaffe in 2018, where they investigated trends in high impact aerosol events, or trends in 98th percentile. And they looked at PM 2.5 from the improved network on the left there, and aerosol optical depth from MODIS. And I want to highlight where the trends are not the same, which would be over the Great Plains here, where we see positive trends in AOD over the Great Plains, but negative to negligible trends in surface PM 2.5 measurements. This indicates that there are spatial discrepancies between what we're observing in column and surface trends. And our hypothesis before beginning this research was that that may be due to dust in the column. To investigate this, I used a couple ground-based observation networks. The first would be IMPROVE, which provides 24-hour aerosol samples every 3 days. And to analyze dust there, I focus specifically on the PM10 minus PM 2.5 product, or the coarse mode aerosol product. And the second network was the AeroNet network, which deploys CML sun photometers, providing measurements every 3 or 15 minutes of aerosol optical depth. And they also have include a spectral deconvolution algorithm, which takes the bimodal or sometimes trimodal assumption of the aerosol size distribution and the curvature of those optical properties to separate the fine and coarse mode of aerosol optical depth. So I took advantage of that and used the AOD coarse mode to analyze dust there. And I also included data from the MODA sensor for the Terra satellite with the aerosol, gridded aerosol product that they provide. And to look at dust observations, I used the Angstrom exponent, which I believe Dominic talked to us about a little bit, but that is inversely proportional to particle size. So the threshold that I used here was 0.75. All observations below this, I called AOD dust for simplicity. And it turns out that for observations below this threshold, the seasonality in climatology resembles quite closely to what we expect from literature for dust in the United States, which is a springtime peak in the west and northwest and northern Great Plains, moving to a summertime peak in the south and the southern Great Plains and in the southwest. And we also see what we expect, which is highest values in the Intermountain West and Southwest, which gives me a good deal of confidence that this is a good proxy to look at dust in the United States for trend analysis purposes. And so because environmental data is typically non-parametric, I applied the sense slope to get the regression coefficient, as well as using quantile regression applied to the improvement AeroNet data at the 0.9th quantile to look at high impact events, as McClure and Jaffe did in their paper. Of course, this comes with limitations, which is that the improvement AeroNet sites vary in temporal coverage between the networks and also between the sites. And further, the temporal resolution is different between AeroNet Improve and MODIS, which is important when we consider that dust emissions are often an intermittent event. And finally, meteorology, hydrology, and climate do have important influences on soil stability and dust emissions, but those are not fully considered or represented here, especially in this 15-minute time frame that I have to share with you. So the first result and kind of the foundational result that we'll use to base the rest of my talk on are these trends from MODIS AOD dust from 2000 to 2018, where we see spatially consistent, positive, and statistically significant trends in the Great Plains and Rockies states. And those are the regions that I'm going to focus on today. These increases reach as high as 5% change per year, or almost 100% change over the 19-year period. And so I will be focusing first on these Great Plains states and how agricultural expansion may be influencing these dust emissions in these states. So I've included a photo here that I think is nice to picture moderate to strong winds moving over these surfaces. And I think we could assume out of the grassland on the right or the cropland on the left, which is more likely to produce dust emissions. And this is important because we've seen rapid grassland to cropland conversion in the Great Plains, spurred initially by the biofuel boom in the late 2000s. And it's important to remind ourselves of an event in the 1930s, the Dust Bowl, which arose from human land degradation through poor agricultural practices that contributed to dust storms and amplified a drought. And so this desertification process is something that's important to keep in mind when we consider the grassland to cropland conversion process that's happening. So to look at this, I employed the cropland data layer, which is a cropland classification product from the USDA. And the results for that are here. Just on the left is just a subset of the MODIS AOD dust trends, looking at the Great Plains. And then on the right, we have our results for cropland coverage change from the CDL product from 2008 to 2018. And we see that cropland coverage has increased quite a bit for all Great Plains states above Oklahoma or north of Oklahoma. And those changes have reached about 10% in some areas of the Great Plains. And to investigate how these might be connected, I employed a lagged correlation test where I displaced MODIS AOD dust trend results relative to the cropland change results, and found that the correlation coefficient and statistical significance were maximized to the northwest, which would suggest a downwind influence from agricultural expansion on dust to the northwest. And to further support this, I looked at monthly 0.9th quantile trends, looking at March, June, and October, which happen to be planting seasons and harvest seasons for corn, soybean in June, and then soybean corn harvest and winter wheat planting in October. And here these figures show improve and AeroNet sites trends in the course mode. And we see that in the Southern Great Plains, trends are statistically significant and positive throughout these months, reaching 5 to 10 to 15% per year in increases. And I would like to focus on this site here, Ames, Iowa, the AeroNet site, which is a negative trend in March, changing to a positive trend in June, and may have something to do with the change to soybean planting season, which typically occurs in June. And dust emissions have been shown to be associated with planting and harvesting seasons. So these 3 months are associated with those seasons. Next, I'll bring us back to the foundational figure here of MODIS AOD dust trends. And instead, we'll look at these Rockies and Northern Great Plains states where we're also seeing increases in dust emissions, and relate those potentially to oil and gas development. Again, we can imagine as moderate to strong winds move over this region, which points are more likely to produce dust emissions. And this occurs because construction and maintenance of the well pads and single lane roads for each pad reduce soil stability and lead to soil wind erosion susceptibility. A lot of this occurs because of dry biomass removal, in addition to ongoing vehicle and construction traffic. And unfortunately, the reclamation process is just not well defined or enforced for well construction. Once a well is plugged or stops production, it can still take up to 60 years for that surface to be revegetated. So this is a compounding issue. So I used oil and gas well data from enverus.com to look at that. And on the left here, we have the wells constructed from 2000 to 2018. And on the right, we have how the results of a correlation test between the annual frequency of MODIS AOD dust observations and the annual frequency of well construction by each MODIS grid tile. And we don't see much in the way of statistical significance in Wyoming or Colorado, perhaps due to the complex topography there. But as we move into flatter, more consistent topography, we do see high correlation and statistical significance, especially in eastern Montana and western North Dakota, where, yeah, thank you, where oil and gas wells are densely packed from the 2000 to 2018 region or time frame. So all of this would suggest that dust loading has increased substantially during the last 2 to 3 decades over the Great Plains and Rockies regions. These increases have reached almost 5% per year across the Great Plains and Rockies states in MODIS AOD dust. And high dust loading events have also increased in the Great Plains, especially in the Southern Great Plains. And these increases occur in the months that are associated with crop planting and harvest seasons for predominant crops there, like corn and soy and winter wheat. Temporal and spatial correlations also indicate potential contribution of the recent energy development growth and agricultural expansion to dust emissions in this region. And these increased dust emissions due to these land practices would have direct impacts on health, visibility, water resources, radiative forcing, and environmental policy. And furthermore, just to relate this back to the Dust Bowl and desertification process that I was talking about, especially in the Great Plains, these increases and potential connections to agricultural expansion represent a threat of desertification in the case of any heightened risk or increased drought risk in the Great Plains due to climate change. So it would be great if we could employ some de-incentivization policies and improve comprehensive and enforced reclamation efforts, and also improve the existing policies that we already have to mitigate any of these risks that I talked about above. And I'd just like to acknowledge those who have funded this research, and especially my co-authors, and especially my advisor, Dr. Gannett Haller, for her fantastic mentorship throughout my graduate school career. And I'll just leave it at my summary slide, and thank you for listening. I'll take any questions.
Okay, thank you, Andy. We do have a question from the audience. The question is, could you explain the shift to the northwest between converted grasslands and modus AOD? Seems dust would tend to move eastward generally in that part of the world.
Right. Let's see with this lag if I can get to, okay, here we go. So in order to try and explain it a little bit further, I have employed a bit of meteorology analysis, and these are just some National Weather Service stations where I look at the top 3 most frequent wind observations or wind directions for the Great Plains area. We do see a strong southerly component, which may explain the northerly or the north shift a bit. And we do see some southeasterly components as well, which may explain that. And it also could be a seasonal thing, where in the spring and summer, we especially get the southeasterly wind component. And I should say that these are for wind observations greater than 5.5 meters per second. So focusing on the moderate to strong wind events. And that's the explanation that I have so far, but it is lacking somewhat in the southeasterly component that you would expect.
Okay, we just got another question in. I might have missed it, but overall, how much of the dust increase over the Great Plains could be attributed to oil and gas versus agricultural practices? Seems that policies might be needed for both.
Right, yes. So I did talk briefly, I guess, about oil and gas, and there was some overlap in North Dakota, where there's quite a bit of oil and gas development there. And that also happens to be where the oil and gas development is. That happens to be where we see the highest statistical significance in that state. And additionally, in Oklahoma, where we are seeing increases in dust, we're not seeing increases in agriculture. And so oil and gas, which is prominent there, may also be contributing. So we need to address both, certainly.
Okay, we have one more question. How many years do the numerical models need to run after land use change to say that these effects are due to the changes and not just noise?
Could you repeat that question one more time?
Yeah, the question is, how many years does the model need to run after land use change to say that these effects are due to our changes and not just noise?
So I haven't used any land use models, so I'm not quite sure how best to answer that. But I'd say it's a very complex set of contributors. That land use is certainly not the only contributor. As I said, there's likely a large contribution from climate and soil moisture, and some modeling would be helpful to look into that more, but I haven't done any land use modeling with land use at all.
Andy, thank you so much. Really appreciate that presentation, and we wish you the best at the Naval Research Lab.
Thank you.
You're welcome. And thank you to all of our presenters, to Chris, John, Guillermar, Dominic, Maria, and Andy. Thanks for staying on time and also for your excellent presentations. I want to thank our question moderators, Laura Riamaki and Patrick Sheridan, and also to all of our attendees for joining today. Thanks so much for being here. I noticed at one point we were up to about 130 participants, which is excellent. The recording of all presentations will be made available for future viewing, and that will be on the eGMAC website where you registered. Also at the top of the agenda for today's session, there's a link to that website. Next week's session will take place next Monday, so that's a slight departure from the Friday norm that we started, but they will be on Mondays and Fridays going forward. So please look at the schedule in advance so you don't miss one. But next week's is from 8:30 to 10:30 Mountain Daylight Time, and it's this coming Monday, June 22nd. And the session theme will be understanding atmospheric concentrations of trace gases affecting ozone and climate. And during that session, we'll hear from 7 presenters. I also wanted to say just a few words about today. Today is June 19th. It's also known as Juneteenth Day. It's a long-standing holiday in the African American community, marking the emancipation of all slaves in the Confederacy. And I encourage all of us to celebrate today, to recognize our history and our culture, and also to embrace all people and listen to all perspectives, as we've had a chance to do today, and to ensure that we banish unjust treatment of all people, and so we make a positive change in our own spheres of influence. I think we're really fortunate that we all have the freedom to pursue our science and also our dreams, but we also have a responsibility to ensure that all people have equal opportunities and they're treated fairly so every person has a chance to pursue their goals. So I just wanted to mention that as Juneteenth today. And I really look forward to the presentations and the discussions that follow in the weeks ahead. I hope that you all and your families have a just and an enjoyable and a peaceful weekend. Thanks so much for joining. Bye-bye.